Good afternoon. My name is Rosaura Lopez, Director of Postgraduate Studies, and I would like to welcome you to this platform created to share ideas, perspectives, and opinions about different subjects, which is formulated from the Postgraduate Studies of Art, Architecture, and Design from Universidad de Monterrey, with our headquarters at Centro Roberto Garza, Sada, the gate of creation of Latin America. Before we start, I would like to inform you that this session will be recorded. Also, at the end of our speaker's presentation, we will leave a few minutes to Q&A, which you can begin to share with us in the box below. Tonight, we have our second season kickoff with a very special guest, Eric Joneson, Vice President of Technology of Lansmont Corporation. Thank you so much, Eric, for being here with us. It is such an honor to have you.
Thank you. Thank you very much. And thank you for the invitation. Good evening, everyone. I know it's evening where you are. I'm actually presenting from Monterrey, California right now. It's not Monterrey, Mexico, but Monterrey, California. So I appreciate this opportunity to speak to you a little bit about what my company does and what I do in my role as part of the Lansmont Corporation as it relates to distribution, measurement, and simulation. And when we talk about that, Lansmont Corporation is a shock and vibration company. We really kind of specialize in expertise associated with those two types of dynamics, all the dynamics that are present in the supply chain or the distribution environment. And so we focus on kind of measuring or understanding those dynamics and then using those measurements to drive testing or test development in a laboratory using physical testing equipment. So I'm going to talk a little bit about that and give you some examples of some of the projects that I work on. I am involved in many kind of responsibilities for my company, but we're actually a very small company. You might not realize that, but we're about 55 people only in the Lansmont Corporation. So although I have a title of Vice President of Technology, I do many things, including measurement myself, going in the field and doing measurement within the supply chain. And so I have good examples to share. I hope that you'll find that interesting as we move forward. A little bit about my company. We were founded in 1971, which just so happens to be, since it's 2021 this year, it means that we're in our 50th anniversary year, which the literal anniversary date is in July of this year, but we are celebrating a 50-year anniversary, which is actually pretty a long time to be in operation. I have myself been with the company for 32 years, so I am a packaging graduate myself from Michigan State University in Michigan, which is where I live. I've lived many different places in my career with Lansmont, including here in Monterrey. So I travel quite a bit. But I started was hired to Lansmont Corporation right out of college as a packaging graduate, and have been with Lansmont, for 32 of its 50 years. And we practice what the way we describe what we do is this by what I'm showing kind of in the bottom of the screen as this field to lab methodology. And basically it means measure the hazards in the dynamics that are present in the supply chain and use those measurements to drive the type of testing you perform on your equipment in a laboratory. And so we offer, a range of technologies and solutions that cover that whole spectrum, but we also offer all of it. And many times companies will purchase not only the instrumentation side of things, but our equipment, and so then they basically practice that same methodology themselves. And some people bits and pieces of that methodology, but some people all of it, depending on the type of company that or industry that we serve. We, as I explained, we're kind of known in the packaging or package testing community, which is what you see at the bottom of the screen. We make all the different types of equipment that you use in package testing: drop test equipment, compression, incline impact or side impact equipment, and what we call mechanical shakers or rotary shakers. And then another category of equipment that I show at the top is called vibration and shock test systems. And the reason I separate that out is because that type of equipment is really used for what we would call product testing in the product development process. So meaning their products in their development or design process, before they ever get put in packaging, protective packaging, there's a lot of testing that takes place to assess what we call the fragility of those products. How durable are they? How robust and strong are they? So that we know, as part of the package design process, if we know our product is this durable, maybe we don't need so much packaging. But if we have a very fragile product, like a dishware or plates, glasses made out of glass that are fragile, maybe they need more packaging, protective packaging, because of their design characteristics. So we, over the period of my company's existence, I'm going to say that about half of the equipment that we've ever sold goes into the product testing side of applications. And so you can think of companies like Apple Computer, Google, Sony, LG, Intel, Microsoft, all those kind of consumer electronics companies that make kind of complex, maybe more complex products that are highly valuable. There's all kinds of shock and vibration work that takes place to basically validate the designs, the durability of those designs. So we get involved in not only product testing, but package testing, and in many times those functions within companies are related to one another. The product testing laboratory is right next door to the package testing laboratory, and they kind of collaborate or work together. We work in all different markets or industries, as you can imagine. From a protective packaging perspective, it really doesn't matter what you make. You typically make it somewhere and then you ship it somewhere. It's made in one location and used in another, and so that means that it has to be distributed or transported from the point of manufacture to the consumer, the point of use. And so we, something that actually I enjoy quite a bit is that our technologies are used in all these different industries. So we get to see those different industries. We were founded in 1971 based upon research that was taking place at Michigan State University. And it was research that was taking place at Michigan State University School of Packaging in partnership or in collaboration with a naval postgraduate school that's based here in Monterey, California, that focused on shock testing as it relates to communications equipment on military vehicles or ships or ocean-going vessels. And so this theory of shock testing for product design from the military aspect, one of the leaders of this naval postgraduate school contacted people at the Michigan State University School of Packaging and said, this application, the technology of shock testing, sorry about that, works not only for the design of military or defense products, but also for commercial off-the-shelf products. And so there was research that started to take place between Michigan State University and this Naval Postgraduate School here in Monterey, California. And that was the foundation of my company, and that's where the name comes from. The Lands in Lansmont comes from the city of Lansing, Michigan, where Michigan State University is located. And the Mont in Lansmont comes from Monterey, California. So that's a little bit of trivia associated with the beginnings of my company and how and where we were founded. So our Lansmont Instruments, this is the kind of part of the field to lab. What the technologies that we use to measure or characterize the supply chain, the dynamics and the hazards in the supply chain. We use these devices that are basically shock and vibration data recorders. They also record temperature, humidity, atmospheric pressure, which is really altitude. They can record light, meaning if the door is opened or closed, it has light sensing capability. They record GPS. And we use these devices to kind of, again, measure everything that happens in the supply chain so we can thoroughly understand the severity of those types of dynamics. Do they experience impacts? Are packages dropped? How severe is the vibration in a truck versus a vibration in a rail car or an airplane? What is the handling like when ocean containers are loaded in the ports onto the ship, off of the ship, maybe onto a rail car? All of that information is critical to understanding what then you need to do to simulate that environment, that same supply chain channel, let's say, in a laboratory. So it's hard to get a perspective on what these devices look like or the size of them. I have one, but not in this room, I apologize. But they're small. The smaller ones that you see there in the pictures, they're basically 3 inches by 3 inches. The bigger one is 5 inches. So it's not much bigger really a footprint than, say, a mobile phone. And there are many different ways to use these, but you can attach them directly to the vehicles themselves, to trucks and trains and airplanes, or you can put them in packages to understand the relationship of what we would say is the input dynamics coming from the transport vehicles or the transport mode, and then we want to understand the responses of the packaged products to those inputs. So there's rationale for why you would do both of those scenarios, attaching these kind of devices to vehicles and attaching them directly to or inside of packages. This is an area that we've been started for us back in like 1994 or so, and these are some of the new instruments that are coming out even now, which are even more kind of developing more and more sophisticated ways of interfacing with these instruments. So for instance, what used to be you had to talk to these type of instruments through cables, through computers. Now we can talk wirelessly with Bluetooth to set up, communicate, download the data, get reporting directly from the instruments on mobile devices. So you basically a quicker way to get to the answers or the information of interest when you do these types of studies, when you need to know immediately versus waiting to process data, analyze data, and report on it. And so the different ways we use these devices are what we call monitoring applications. And so that's a very specific type of an application, which means that these are less, comparably for us, less sophisticated instruments. They basically only record things if and when something bad happens. And what that means is that if someone has a product, whatever that may be, and typically for these applications, they're expensive products, if they know that product can see no more than, say, 10 Gs of impact. That's a measure of acceleration. That's how we describe the impact severities. It could be from a drop, it could be from going down a chute in a sorting facility, but when things hit each other, they experience some type of an impact that's described in Gs. So many people with valuable products know that my product can only see plus or minus 5 Gs in this direction, and maybe only plus or minus 2 Gs in this direction, and maybe only plus or minus 1 G in this direction. And so all they care about when they do these kind of studies is to know if and when those critical levels were ever exceeded. And so many times when people do these studies, the instruments actually don't record any information because nothing bad happened. And that's okay, because they only are used for, tell me if and when something bad happens, and when that does happen, I need to know all the information that surrounds that event. I need to see all the raw data to describe that event. So that's kind of a monitoring application. And this is a real picture now and a real example of the use of these types of instruments. So this is a train, and what you can see there was a derailment, and this is a real customer of ours, and that customer is NASA, the space agency here in the US. And inside each of these rail cars, underneath these covers, is a segment of a rocket booster. and they're very sensitive, obviously. And so NASA, what they do is they attach these types of devices to all of the components and hardware that they ship around on land before they ever get assembled into what they would launch into space. And so what happened in 2007 is there was a train derailment. So these rocket segments, believe it or not, are made or manufactured in the state of Utah, here in the west of the U.S., and then they ship by rail cars all the way down to Florida, where the Kennedy Space Center is located, which is about 2,600 miles. They ship all that way by rail, and then they're taken off the rail cars and then assembled into many different of these segments that you see in those white covers into a rocket booster that then gets launched. This was back in the days of the space shuttle. These were used to launch the space shuttle. So these had instruments on them, these types of devices, back in 2007, and they weren't our devices. But what happened was the devices did not trigger in this case, meaning they missed recording the events. Now, you didn't need a device like this to tell you that a derailment occurred. It's pretty obvious there was a problem. But what NASA wanted to know is, even though the train derailed, some of these containers didn't tip over. And so they wanted to look at the information on a recorder like this to say, is this one okay? Is this one okay? Or do we need to fix them or do some type of remediation work with those segments? And because those devices never triggered, that caused a big problem for NASA, which then led them to us. And we started doing a lot more work with them. And that continues today. We're quite involved with NASA in monitoring specific applications like I'm talking about here. So only wanting to know when these kind of critical thresholds are exceeded in their supply chain. So yes, I'm talking about rockets or segments of rockets, but from a packaging perspective, it's the same. It's completely relatable to what people who work at maybe Procter and Gamble or Unilever or any other type of Pepsi, Coca-Cola. It's the same type of dynamics. It looks different, the size and value of the items here, but in the reality is it's the same type of dynamics. It's rail cars going down rail tracks or railroads, and they experience shock and vibration. So it's the exact same type of measurements. Those same customers use this type of technology, but I'm giving you the example here from the NASA or the space stuff, because it's also very interesting to see. This is our real pictures. This is current. This picture was taken within this last year. That is what the picture that you see there is what's inside this, underneath that white cover. This is a segment of a rocket booster. And if you look at this picture on the wall behind here, you see this is a huge rocket segment. And then there are two white boosters on each side of that massive tank here. And each one of these boosters is made up of 5 of these. So there are 5 of these stacked up here, and then there are 5 more stacked together here. And our instruments are attached to every one of those that travels as they move from their point of manufacture in Utah to the Kennedy Space Center. Some of these also move from Utah out to Southern California, where there's another launching facility. And whenever they're moving, they're being monitored with our instrumentation. So this is one example of what that looks like on a rail car. This is another example of that very large center section. This big section here in the middle. That's basically what this is. And our instruments are attached once again as these items move. This is a space capsule. It's hard to see it in this picture, but there's one of our instruments here. So our instruments are very heavily deployed in the space program, but they don't measure anything associated with space flight. It's all about getting the space hardware from wherever it's made safely transported to the launch pad, just to make sure that it gets to the launch pad. So as all these big, sophisticated, expensive pieces of hardware are moving around, I often look, I watch this stuff constantly. So I am impressed by the pictures of the big space hardware, but my focus is always getting close to the screen and looking for the little evidence of our instruments. So in this case, if I was able to zoom in on this, you would see there are 3 of our instruments, again, attached there. We're on everything from a quality perspective to make sure that those pieces maintain their quality or integrity during transport. It's just a video that shows that same thing. You'll see some of the pieces. Hard to see them, they're small, but they're there. I'll keep moving. Sorry about that. Okay, so moving to the other, so now this looks like a similar kind of slide that I showed earlier, and there's only one word that's changed at the top, and it says measurement applications. The other one said monitoring application. What measurement applications mean is that the same types of devices, but they're a little bit more sophisticated in their overall capability. They record, instead of only when big bad things happen, they record everything, these types of devices, whether it's good or bad. When you ship something from point A to point B, they record everything from the second you turn them on to the point that you turn them off. And these are more like research kind of grade instruments, so that they are able to characterize everything that takes place, whether it's significant or insignificant. They also are recording, like in these cases, they're recording all the climatic conditions, temperature, humidity, atmospheric pressure, potentially GPS, and all these other type orientation. If things if they're shipped in this, if you can see my phone, if it was shipped in this orientation, like assume that was a package and somebody turns it on its side, on its way, and they weren't supposed to do that, we're able to record that kind of information as well. And so these devices, instead of recording, let's say maybe 10 to 100 different types of events that occur in the supply chain, these can record tens of thousands of those types of individual measurements as things are being shipped around. And they can also run for as long as 3 months, 90 days, sometimes even 120 days if it's international shipments. So they're much more kind of same type of technology, but they just really, what the difference is they record everything that takes place. And these are what are used to, for instance, to develop things like vibration test profiles that would be put into a laboratory test piece of equipment to drive that machine to simulate a specific mode of transportation, whether it's truck, rail, intermodal rail cars, airplanes. That all takes place from data that's captured on these types of devices. This is just to give you a screen capture of one of the ways that we look at the data when it comes back from our device. This is real data, just one way of looking at the data. So if you look from left to right, what this is it's hard to see it, but I think this says something like August 4th, and this might say August 5th here. And so this is basically 1 day's worth of data from left to right. And each one of these red bars, the height of that red bar is an individual event that was recorded by the instrument. And the height of it is associated with the severity of the event. So what that means is that nothing was happening here, as maybe for like an hour. And then the instrument sensed some type of dynamics occurring, vibration. So there was some type of transport. It was moving here, then it sat for a while, moved a little bit more, moved a little bit more, nothing in this area, and then movement, and then some higher amplitude movement, and then not much out here. At the same time, what we're recording is temperature and humidity. The yellow is temperature, the light blue is humidity or relative humidity, and then the blue is altitude, based on an altitude sensor. So what that we record that for is, so this was an instrument that was in a package that was shipped from Indianapolis, Indiana to Rochester, New York. And it was for Eli Lilly, who is a biological or pharmaceutical company here in the US and based in Indianapolis. And we put a sensor in a package, shipped that package by FedEx from Indianapolis to Rochester, New York. And what we were doing was trying to understand that when packages are delivered by aircraft in the air, what does that look like from a vibration perspective? And so by having these kind of devices, we can quickly zero in on the data of interest to say, this is when the flight took off, this is when the flight landed. So we can kind of focus our attention on the data in the red portion that was recorded while the plane was in flight. And what we're able to see there in that case is, in this example, is the vibration was not very, compared to the road, getting it to the airport and taking it from the airport or around the airport and on the tarmac as it was being moved in and around the airport in New York, it was worse, right? The height of those bars is much higher than anything that we see in the air side of it. And then what the data that we get from all those red bars, we use to create what are called power spectral density plots, PSDs. And these are the type of plots or data that you can input into a vibration test machine in a laboratory and use to drive that test system. So I can simulate that blue data that was captured from the tarmac at the airport. I can basically play that back on my vibration test system. I could also do the same thing for the aircraft. And what this kind of a plot shows you is that the tarmac vibration was much more severe than anything this package saw when it was in the airplane during the flight from Indiana to New York. And so that's how we use this kind of data. And so we do these kind of measurements from what you can imagine, all the different modes of transport, truck, ocean, rail. And what we really do is we focus, not so much on the vehicles or how the vehicles ride, but we're really most interested from a packaging perspective of what's going on inside the vehicles, the transport vehicles, where the packaged product interfaces with the transport vehicle itself, which is usually the floor of a truck trailer, the floor of a rail car, the floor of an ocean container, or maybe the cargo floor of an aircraft. And so this is, an example of a real measurement that was taking place with those types of devices. This is a little bit more sophisticated setup, but this is really, why are we measuring here? Well, because when we put the packaged products on a vibration table in the laboratory, this is what we're simulating. We're simulating the floor of the transport container. So we want to make our measurements from, in this case, from that very specific type of location, that same interface location. These are examples now of those same types of instruments, but being attached not to the vehicle, but to, you can think of this as a package decoy. So this is what we call a decoy, or a dummy product is another way we would describe this, where we put the instrument in a frame, a footprint of a product. So if someone has a product of a certain size and a certain mass, and they want to know how that product is handled, when shipping through UPS, FedEx, DHL, they can create one of these decoys and then package that decoy. So this is looking down, that's that same decoy, but now we're looking inside of a corrugated shipper with foam corners around it. and they'll close this up, and then they'll ship this around, and we're able to characterize what takes place in those types of supply chains, the parcel supply chains, maybe even the Amazon type of supply chain, to know how things are handled. Are they dropped? If they're dropped, how high, how many times, what orientation, what does that look like? And so that's an example of what we would call a decoy. And this is just kind of an example of when we were designing a decoy like this and testing it in the laboratory, so that we could kind of understand, if we create this decoy, we put it in a package, we drop that package from 1 meter or 2 meters in different orientations, what does the instrument record? And once we understand that from a controlled laboratory input perspective, then we can ship that same decoy out in the supply chain, and then compare the measurements that we capture in the field to the known measurements or inputs that we generate in the laboratory. And then we can say, oh, the supply chain looks like this versus what we're doing in the laboratory looks like this, or maybe it's the other way around. We test at this level, we dropped our packages in the lab from 36 inches, but in the field, I never see anything more than 24 inches. And so it's a way for you to assess the kind of hazards of what's really going on in your supply chain, and then allow you to make decisions about how you're going to use that from a testing perspective. Are you going to match that? Are you going to over-test? Are you going to under-test? And that's what people do with these types of studies. Just another picture of another decoy getting ready. And then this is yet another example of a measurement setup. And this is something that I get involved in quite a bit, more of the unique or high-end measurement projects. So these are plastic pallets. These are what would be called beverage pallets. It says AB on these. That means Anheuser-Busch. So these are pallets used by Anheuser-Busch to ship beer, canned and bottled beer, through their supply chain, which is typically a refrigerated supply chain. And so this top pallet that I'm showing here is one that's flipped over. It's upside down, just so you can see the way the instruments were attached to the pallet. There's one in this corner. There's something here. It's hard to see it because way down over at this end, you can't see it. But there's another instrument in this corner and one in this corner. So there's really a measurement taking place simultaneously from all 4 corners. And in this type of a setup, what we're able to do is not only measure if the thing is moving up and down during transport, or if it moves side to side, or if it takes an impact on the side. We're actually able to measure this kind of motion. I don't know if you can see me or not, but it's what we would call a multi-degree of freedom motion, or 6 degrees of freedom, because in the real world, that's how dynamics actually occur. And so you can, what I'm doing is you can, my hand is rotating, and you can think of a pallet. It's not as dramatic as what I'm showing, but that's how things really do move. And when things move like that, you can think of beer or a beverage being heavy, liquid. It's liquid. It flows. It meaning that you can't really contain it that well. It likes to slosh around and move and generate momentum. It's also very heavy compared to other types of products. So when you have a really tall stack of product like this, the loads of these pallets are very heavy. And if you put in while the thing is going, the truck is going down the road, or the train is going down the rail, and it's shaking, if it's shaking and also shaking with a side-to-side input or a lateral input, these loads want to do this. And when they're tall and heavy, the taller they are and the heavier they are, the more likely they're going to move, and more severely they will move. And so this is a problem for people it can be a problem for people in the beverage side of the world. So Pepsi, Coke, Modelo, I've done projects in the past for Modelo many times. And it's a challenge for them to contain these loads. So they use things like stretch films. And if you look at like these middle loads, these are obviously in fiberboard cartons, the cans, and stretch wrap. But over here, you see there's no fiberboard carton. So there's less structure in this load as compared to this load. So that means there's more of a dependence on the stretch films for packaging to contain that load. And so these guys have problems from time to time with their loads moving too much, and sometimes tipping over. They shift and sometimes actually tip over and collapse. So what they wanted to do was measure those dynamics with a large study. And to really accurately measure those, we had these what we call smart pallets. So it's hard to really see it, but there's instrumentation around the whole base of these pallets so that we can fully understand not only the up and down kind of motion or vibration, but do these things really start to move or dance in these different modes of transport? And then they use this to drive the type of testing they perform. This is the same type of a setup. This is a CHEP pallet. So it works with beverage pallets, but we also do this with CHEP pallets. And this is a real example of a project that I worked on with Procter & Gamble. So instead of now beverages, these are paper towels, and they're really light compared to really heavy liquid products. These are really light. A pallet load of these is only like 300 pounds versus 2,000 pounds for the beverage. So you'd think maybe this isn't such a challenging problem, but it is more because of the what's interesting here. This is a real example, and it was a real problem. A roll of paper towels is round, right? It's obviously round. And if you look at this bottom pallet here, you can see no matter what diameter you make of that roll, it's never going to use the full footprint of the pallet. So there's this gap here at the base of the pallet. And so that creates challenges from a stretch wrap perspective, is how do I get my stretch wrap, make contact with that load to hold it in place? So it can cause really big challenges of how much tension, the material performance of the films itself, how do I get that over there to hold that entire load in place? And so what happens, because there's a lot of tension there at this point of contact where the film contacts the pallet, there's a lot of stress. And often for them, that means that the pallet will poke a hole in the film. And once that happens, the whole load loses its containment. So it's not so much that the pallet or the paper is heavy or it wants to move, but once you poke a hole in that film, it's free to move, and it moves, and they walk around, and it became a big problem for these folks. And so they also did a large study. So in this case, you can maybe see here that this is instrumentation on a pallet, and there's also instrumentation on the top pallet, and instrumentation mounted to the floor. And why they did that is because in this case, they wanted to understand what are the dynamics that the truck is generating. So that's what we measure here. What is the truck doing? And then from that, they wanted to say, well, then when that happens, what is this pallet doing? Basically the first pallet loaded on the floor. And then at the same time, I want to understand what the top pallets are seeing. Is there some relationship that says if I put in X here, do I see 2X here and 3X here as far as the severity or the amplitude? So these folks did a very large study looking into that of cross-country shipments from the East Coast of the United States to the West Coast with the same intent to not only understand what was going on, but to then use the information from these studies to drive their laboratory testing, where we had the capability to simulate all those very specific dynamics. So this is just another one. Orange juice being loaded in Florida. That's a smart pallet going on the rail bed. And these are the types of projects that I get involved in quite a bit, where I travel and help set them up and get things installed and documented. as to how things are loaded. So this is a smart pallet here. This is another one here. And yeah, this was rail cars that were traveling from the south of Florida all the way out to the Pacific Northwest in the state of Washington, almost like a 3,500 mile journey. And the same kind of issues. They have problems with load stability. So they wanted to understand the dynamics. So this is a lot of examples of real projects that I get involved in with many big companies that, global product manufacturing companies. And then this was me, actually maybe a month, not even a month, but just a few weeks before the pandemic hit. I was actually in Brazil last February, a year ago, February, doing the same type of measurement, not just here in North America, but in Brazil. So for Ambev, which is, division of Anheuser-Busch, or AB InBev. And so we did the same thing, instrumented pallets, but now we're trying to, what Anheuser-Busch was trying to do was create a library, or AB InBev, a library of what the supply chain looks like in North America, what it looks like in South America, what it looks like in Europe, and what it looks like in Asia. And so this was the after kind of doing all this in North America in different areas, we did this in Brazil. And things, when you move around the world, you see some of the things you assume about the supply chain or how things are loaded and unloaded are not necessarily, at least from us here, in the US, it's different from maybe what we think is, quote unquote normal. This is a real, truck full of Anheuser-Busch product, lots of pallets. We don't see these kind of trailers here in North America. I'm not sure if you do in Mexico. Not only that, this is a very long truck, longer than what we would use here. And we call these, I guess, one of the ways we refer to this as a curtain sider truck. So there's no sidewalls to the truck. There's no rigid wall to the truck. These curtains, so the product can be loaded and unloaded from the side like this. And what the problem with that, not a problem, but some of the concerns with that are that these products, the unit loads, if they're not stable, or if they have potentially can tip over from insufficient packaging, becomes now a safety issue, because those loads could fall outside of the vehicle and potentially hurt somebody, in another car, passing car, someone walking down the street. So there's a lot of effort, and there's even regulations in Europe about how stable loads must be. You have to validate their load stability in a laboratory environment before you ever put them in trucks. So it's important to, again, understand what those dynamics really look like, not only from the up and down, but from the side to side. So if a truck goes around a corner, turns a corner, and they turn it too severe, or they're going on a roundabout, will that load ever potentially shift and fall outside of that vehicle? I'm going to skip through this one real quick and just explain now some other things I think that are interesting. I hope you find this interesting anyway. My company is part of a group now. Back in 2015, we were acquired by a venture capital firm. We had been privately held ever since 1971, but in 2015 we were acquired, and we joined what's called the Noise and Vibration Technologies Group. And the two other sister companies to Landsmont focus on the common denominator between the three companies is vibration measurement and vibration testing, but kind of different specialties within each of those, the two other groups. This is the names of the two other groups, Data Physics and Team Corporation. So just again, the common denominator between the three is vibration measurement and testing. Landsmont in the middle focuses primarily on people that are some way or the other dealing with or focusing on packaging or transport of goods. Data Physics focuses more on just product testing, which means very high frequency durability testing from a vibration perspective. And then Team Corporation focuses on on what we would call multi-axis or multi-degree of freedom vibration testing technologies. So when I was moving my hand like this, package testing today is mostly the tables go up and down like this. That's all they do. They might do it in different ways, up and down, what we call random vibration, but that motion is only up and down. But this company, which I'll show some examples, their machines move in 6 degrees of freedom, up to 6 degrees of freedom, more like you would see like at a flight simulator or even at an amusement park, something that is more of a real simulation of a type of transport. It's more real world like. We get involved, my company, not only in the packaging, products for packaging design, but we do some really kind of high-end advanced engineering designs that are a little bit outside of the norm or outside of the package testing side of things. Very large things, very unique applications for shock, which I'll show you here in some examples that you see, like there's a instrumented dummy on a seat here, and you might think, what does that have to do with packaging in Landsbot? And I'll explain that. So this is a video, a real video.
Whoa! Holy shit!
Sorry for that. And what that was an IED blast, an explosion that occurred in the road, and nothing happened in that case. But you can think of an explosion like that as the source of a very large shock event. And since we are a shock and vibration company, we are able to simulate even those kind of explosive events or the energy associated with those with our types of machines. So back in the 2007 timeframe, the U.S. Army came to us and asked if we could build a machine that would simulate IED explosion from that would occur from the side of the vehicle, like what happened in that video. So a blast from the side of the vehicle, and what that would do to someone that was riding inside that vehicle. And the whole idea for this is that why they wanted to develop that type of testing was to develop seat restraint systems. Think of a seat, the straps, the harness, all the protective stuff inside the vehicle that would protect soldiers if any type of those blasts did occur. So it was really about and so we talk about it and we describe that as, instead of like product packaging, it's people packaging, because it's this, you can think of the seat as cushioning, the straps as a type of like stretch wrap, whatever you want to call it. It's people packaging, but in a way it's very similar to packaging. And so we developed this machine back at that time. And again, it was, what they would do is put a seat system on our tape, on the sled, put an instrumented dummy. So what that means is this crash test dummy has sensors inside of it so that they can measure when these types of events happen on the testing input, what was the response to the simulated person, to see how severe it was. And so this is kind of a stretch for us at this time it was. And this is a video showing what this machine looks like when it was being built here. And that might not look all that impressive, but there's a huge amount of energy that takes place there. What you didn't see was a seat, but what this next video is from the lab in the U.S. Army, and you can see in slow motion what that looks like. So that's kind of an example of what the application is in that case. It's people packaging. It's how to protect that person when they're riding in a seat, how to keep them cushioned and not being thrown around. So that's real. And then what we did, I'll try to move through this quickly, but that led to more bigger and larger sophisticated shock test systems that simulated not only the explosions from the side, but explosions that could occur from underneath the vehicle. So Whereas that was one person. You can see here there are 4 people in seats on top of this machine. This is a very, very large machine. That was, I don't have a picture of the finished machine, but we did build this. This machine is over 40 feet tall. So it's like, it's just amazing to me. I'm a packaging person. I can talk about this stuff pretty well, but we have a lot of very talented engineers that can build machines that do incredible things as far as their performance and their energy. Very big, sophisticated piece of equipment. Looks something like this. Same thing, crash test or dummy would be placed on top of this machine. This was actually built in our facility, so tall that we had to cut a hole in our roof just to build it, to allow it to generate the type of energy it needed. So that simulates the blast underneath and what that would be experienced instead of just from the side. Now, what does that look like from underneath? And then the last one I'll show. I'll move on. I apologize, but this is another one that is machine like this that is located at Johns Hopkins University, which is in the Washington, D.C. area here in the U.S. So it's a version of the same type of machine that I'm talking about. But in this case, instead of using crash test dummies on the machine, they actually use cadavers, which means dead bodies, because the response of it's more realistic, I guess, response of the test sample as compared to a crash test dummy. So this is where they store the test samples before they're tested. This is actually not a dead person. This is a person that's working on the equipment, but that's basically what it looks like. And I semi-joke, it's certainly serious stuff, but I don't know about in Mexico, but here in the US, we are able to, when we get our driver's license, we have a place on the back of our driver's license to sign that says in case of an accident and where we're that maybe we're killed, we can donate our organs, our bodies to research, and many people do that because you can, your heart, your lungs, different parts, you can donate those, and so a lot of people do that. It makes them feel good, and I always say be careful, because if you sign the back of your license, you may be tested on one of our machines. I don't know that I'd want to be used for this application. I'll get out of that now. No more talk about explosions. This is another big system. This is a big vibration system, and this is at a NASA facility here in the U.S. called NASA Plumbrook. This is the most powerful vibration system that's ever been built in the world. It was at the time, and I'm pretty sure it still is, much as we know. This is a multi-axis vibration system meant to shake whole segments of rockets. And not only that, but of space capsules attached to the rocket segments. This is a real rocket segment. This is a mocked up space capsule. Normally the space capsule would be attached here too during the test. And so this is a very large system that one of our sister companies, this is not Landsmont, but our sister companies built this. And I've gone to this facility to see this in person, and it's very, very impressive, just massive. And this is some video of what it looks like when the testing is. So you can see the items moving around, and it's hard to really get an idea of how big this whole assembly is, but this, you can see stairs here, you can see a platform, a railing here, so you can kind of imagine a person standing here and just how large this is. It's very large, very impressive, can test very, very big, heavy items, and it's cool. And this is testing of in this case, real space hardware. So they don't, this hardware is so expensive that they can't build test samples in addition to the real samples. So they test the real parts. This is a real rocket segment. You can see where the nozzle, this is looking underneath it, camera from down here in the pit underneath. So this is the real thing. So the testing the way they perform this testing is to challenge the test items, but not to the point where they will damage the test items. It's very important to learn from the testing, but not to damage the products, because the products are the real products that are going to go to space and are very, very expensive. This is a room in that same facility. My company's built. What this is what's called an acoustic reverberant sound chamber. Basically, these are big speakers, sound speakers in the wall. And just to give you an idea again of how big this is, that's that same segment. Here is a person sitting on the floor. So basically, you could walk inside of these speakers or these horns. And what they are used for is generating sound vibration. Instead of shaking it on a machine, it's for blasting the test item with sound. Basically aiming these large horns that put out crazy amounts of energy or sound, acoustic energy, that simulates the vibration that the space hardware would experience when it is traveling at hypersonic speeds, 3,000, 5,000 miles per hour. And there's so much energy when they're running a test in this room. They have a humongous 2-foot steel door that closes in that room, but it generates about 170 decibels of sound energy, which what that means is if you were inside that room when the testing was going on, it would kill you, because all of that energy would cause all your organs, your eyes, your heart to basically like melt because of the intensity of that energy. So it's a crazy amount of energy that takes place inside there. Very impressive. And again, this is a place that I was able to go visit to see all this. And so it's really interesting and impressive. Last big system I'll show you. This is also a big vibration system at a location called NASA Goddard, which is a space research facility in the Washington, D.C. area. And what this machine is used for is testing of what's called the James Webb Space Telescope. So this is a real telescope that's going to be supposed to be launched in October of this next fall. And this is the most expensive item individual item ever made and transported in the history of the world, supposedly. So the value of that one telescope is about $10 billion. And this telescope will be launched out to an orbit 1 million miles away from Earth. Most satellites are about a couple hundred miles in an orbit, a couple hundred miles around Earth. So this is going to go out 1 million miles away. And the reason for that is that it's the farther away from Earth, you get the clearer or the less noise generated from the Earth itself that can cause issues seeing things clearly from a long distance. So this is going to go far away. And what that means is that once it goes far away, we can't go fix it if there are problems with it. So it's you have one shot to get it right, because we can't go send robots or astronauts 1 million miles away to fix a problem. So it's the design of this is very, very critical. And they had to test it. They had to shake it like any other product. They had to go through testing to make sure that it was going to be durable enough to be launched. And so it was done on my sister company's machines with their controlling those machines. So it was kind of a very big deal. This is what it looks like as it was getting ready to be tested. These are all these gold shapes here are mirrors made out of gold, and very, that's the most sensitive part of the whole telescope. And these people are all in clean room gear because they had to, contamination of the mirrors was a big issue. You could very sensitive, could not allow any contamination of those mirrors. So what they're doing is they're lowering a room, portable room, over top of the telescope as they transported it from one room into the test room onto the vibration system. So you can see the telescope is inside this portable clean room being loaded onto the vibration test. And this video kind of shows what that movement looked like. So that's actually the telescope being transported eventually here onto our machine and being tested. Putting it on the table and eventually shaking it, which was a very kind of nerve-wracking or tense time for the engineers at NASA as well as my company engineers, hoping that everything worked the way it was supposed to, and then shaking it like this did not break it. Nobody wanted to be responsible for breaking a $10 million product or $8 million. And so it was a successful test. Anyway, it all worked out very, very well. It was pretty neat to be involved in that project. All right, so why am I, the lead in here is that because of my company's Landsmont association with our sister companies and these technologies, what we did is we said, how can we take advantage of some of this technology and bring that to the packaging community, package testing community? So this is just one more piece of equipment that I'm showing. It's a vibration system. This has got a tank turret on it. So it's a defense testing application. What we did is Landsmont took this design and turned it into a cargo transportation simulation test system. We call it TrueMotion in this case, and it's a multi-degree of freedom test system. So this is one where we took the designs or the technology from our sister companies, applied them to the package testing community, and this now allows us to put things on this very large platform, unitized palletized goods like you see here on that table, and then shake them like how they will experience vibration in the field. And what that looks like, this.
99th percentile.
And so if you notice, in that case, I won't play it again. We just started though, so I can.
99th percentile.
So these are those same paper towels that I showed in an earlier picture in the back of the truck. It's the same product. This is Procter & Gamble. This is a P&G project. These are, this is a P&G engineer here, and there's, other P&G engineers in this room. This is a testing facility in North Carolina here in the US, where they brought, after doing all that measurement work, they brought all that data into the laboratory and used that to simulate in a controlled environment what took place in their supply chain. And then they tested many different samples and configurations of packaging films, different film containment forces, loading different number of wraps to try to address the problem that they were having with failing these loads and allowing them to walk. Can I do a quick check on time? I realize I'm already over by 6 minutes. Should I stop here quickly?
No problem.
Yeah, I don't have too much longer to go, so I'll try to move quickly. I apologize if I'm keeping anybody too long.
Go ahead.
Okay. All right. So this slide just kind of speaks to why we do that kind of work. Why are people doing those kind of studies? Why am I doing more and more of these measurements with people like P&G, Anheuser-Busch, Pepsi, and a number of consumer goods companies? And it's really because sustainability efforts, what that's caused in kind of the design of unit loads, or even secondary primary packaging, is that these companies are depending more and more on films to contain the loads on pallets, whereas before, things that started in corrugated, maybe cardboard, corrugated, where it was strong. You had structure, you had stiffness associated with packaging, these packaging materials. They've become, those structural packaging members have gone away in many cases, or be used less and less to contain packaging, which in some ways is good, maybe because it's more sustainable. But what that means is that it's amplified situations where load stability has become an issue. So now if I'm depending only on the film in this case, and I've got these big heavy loads, they are more susceptible to moving or tipping over, like occurs here, which means damage not only to the product, but also maybe issues from the supply chain. Now I can't even unload this from the truck without having to restack it onto another pallet. It becomes a nightmare for these companies in many ways. And it's kind of a newer problem. It's not new, but I'd say in the last 5 to 7 years, it's becoming a bigger and bigger issue with companies. So this has led to research in groups like este, which Christina for sure is aware of. Hopefully many of you are as well. Standards, writing, creating and writing and maintaining organization that writes testing standards for how you simulate these kind of things. They are undertaking research. This is still going on to try to understand those types of dynamics more and more. And we're part of those kind of efforts too, to help on the collaborative research side to say, what does that look like? What's causing that from the industry perspective, kind of that we can all share and come to a common understanding of what that looks like, so that we can also then come to a consensus on how to simulate that in a laboratory environment. So this is just an example also of some of that research. We've collaborated at este to try to measure say, if we measure that and we play that back, do we get similar responses that we see in the real world? So this was, real example of that type of research where we all measured, we all went to a common laboratory with the capability and simulated that. All right, my last few slides. This is the same examples of the research that I take part in. This is that back to Anheuser-Busch. Examples where we instrument. These are actually intermodal cars, containers, where we instrument. We measure not only with our instruments. A lot of times now we're using cameras. We use infrared cameras. Obviously, the containers are closed. They close the doors. There's no windows in trucks or containers, so there's no light. So we use infrared cameras while we're measuring, so that we can see, when we see these big measurements from a data perspective, what is the load doing inside the containers, so we can understand the response of the loads. So we do these big studies. These are from Los Angeles. In this case, this is one from Los Angeles to Houston, Texas, by both rail and by truck. What did I do? And what we did is we instrumented in an intermodal rail configuration. If you know what intermodal is, it's those kind of ocean containers or sea containers that are stacked on rail cars, and often those containers are stacked too high, one on top of the other. So the higher you get in that situation, when you're way up high, and if the rail car starts to rock and roll side to side, the top one moves a lot more than the bottom one, and can be a much bigger issue. So they wanted to understand what that looked like. So we did this measurement, and this is just examples of what it looked like, not only measuring it, but this is the black and white view from those cameras. The cameras were mounted in the containers, looking at, these are 2 pallets of beer, and this is an airbag, a dunnage bag that is used to kind of lock the load in place. So we measure that. Hard to see, maybe, but notice that the pallets are moving like this, side to side. That's the lower one. You see the higher one moving so much that you can see the sidewalls of the container flexing. These steel sidewalls, you can see that this is moving so much that these are flexed in and out like this. And what that does, because of that dynamic, is it causes the hands to bend and to maybe collapse or fail. And sometimes that repetitive motion over so much time causes the cans to actually fracture and start to leak, which is a big problem. Last videos. This is a truck shipment. This is 2 pallet loads of beer here. Behind these are black plastic separator dunnage pieces. And what they're used for is because these are 2 straps, fabric straps that are used to lock the load in place. So these black plastic pieces are there just so that the straps don't directly contact the packaging. But what happens here, what you'll see is that when the truck is going down the road and it puts on the brakes, these pallets all will shift forward towards the front of the truck. And that's, again, an example of a problem for these guys. So let me just show you what this looks like. Right there. So I don't know if you can tell, get an idea of what happened there. You see, like here, that the straps are loose. Here, they're tight. And that, so this is kind of played back at a faster speed than reality, just to get to the point. But what happens is, as the truck puts on the brakes, it stops, everything moves forward, the straps lose. Now it's not moving, now it starts speeding up again. There it goes. The straps get a little bit tighter. There, just shifted forward. So we want to see that when we do these studies. We want to measure it, but we also want to see it so we can tie the measurement to what happened in reality. And so this is a real picture. We followed those trucks. So eventually, when the trucks arrived, that's what the product looked like when it came off of the truck. And this is really the guy that unloaded it. And you can see how happy and thrilled he is by the problem. And the problem is that sometimes this shifts. So in this case, these did not tip over, but it's shifted so much in the direction of the front of the truck that it can become a safety issue, and that they can't unload them like this. They have to actually go in and restack every one of the pallets. So every pallet in this truck looked like this coming off of the truck. That's not a good situation. So if they don't have to go and restack each of those, what he has to do is he has to unload them and use high technology to fix them, to push it back in place, which is kind of silly, but that's what he has to do to fix them all. And so nothing really is damaged in that case, the product, but what the problem is, it's a safety issue. This is a video that after he does that, he straightens it back up. He takes the pallet loads off of the truck into a cold storage room, basically a big refrigerator where they store. This is a beer distributor. It does not work for Anheuser-Busch. He works for a beer distributor. So they have Anheuser-Busch product. They might have Modelo. They might have, microbreweries, all kinds of different product in here. And they stack that product. And they stack it very high, as high as 3, maybe even 4 pallet loads high. Well, if these loads are not very stable and can shift easily from a little bit of energy, you can imagine that this now becomes not only a hassle from handling, but it becomes a safety issue, that they could fall, collapse, and hurt somebody. So it's a really big deal. So what we do is we try, in these cases, to understand what that. So these are screen captures from our little recording devices, so that we can understand what those dynamics look like when a truck brakes, turns, or accelerates, so that we can use that data to drive machines that can simulate that and do testing. Let me just move forward here this is that, sorry, go back. This is the vibration part of that testing. Kind of throw it around based on data that we measure. Doesn't look all that exciting, but when we increase the intensity, we can get things start dancing around the environment. So you can see how well that works together. So what the changes in the containment of that is. And then we can also simulate those truck braking events to put in those type of acceleration profiles or deceleration profiles to simulate the truck putting on its brakes. So we can see in a controlled environment, are those loads going to stay together? And we can try, they can try different configurations of film, secondary packaging, tray heights, things like that to find the optimum packaging configuration that will work. Cheap, the right cost, but also the right performance, so it holds together. And then my very last slide is this just kind of new technology that we've developed that is better used for simulating those truck braking events. Let's play that, and then I will let you go. Thanks for your patience. This is a new, much more sophisticated piece of technology that allows for programming in those types of accelerating, braking, and turning, like roundabout type of dynamics. And there is a test requirement in Europe that requires this very specific type of testing. So this was built to be able to deliver that European regulatory requirement, but now this is coming more and more for consideration here, at least in North America. But this is a new technology that really focuses on that. So from doing this kind of understanding the supply chain, the dynamics, it pushes us, leads us into developing simulation techniques that better simulate that, more what we say closer to reality. So that's it. I apologize. I'm maybe too much over, and thank you for whoever is still there and stuck with me. Thank you for the opportunity. I hope that you found something interesting in my presentation and what I had to share.
Thank you so much, Eric. I have a lot of notes that I have taken through your presentation, because it is wonderful how from the data collection to the research to the innovation, like all the process that you have mentioned that has been involved in order to develop these improvements in everything. And also talking about, for example, the concept of people packaging, sustainability. I mean, there's a lot of things involved in this subject that the people that are not really immersed in this industry do not see. So it is really all your experience, your kindness to share with us all this information. I have a couple of questions, but if you're okay with this, to let people to continue with their things to do, I will collect them and send it to you via email. So if you have time, so you can answer for us, and then we'll let it know to all the attendees. But honestly, I think this is a lot of things that we have to work on in future collaborations. Yeah.
One thing I didn't mention, what's important for everybody to understand, is that even though there are package testing standards that exist, those standards, even ones that were developed maybe 40 years ago, all were based upon that type of information, that data, whether we were involved in it or not. Which we weren't years and years ago, decades ago. But the reality is there was some type of studies that took place from the supply chain that created all the common test standards that companies and test labs use today. So they weren't just developed out of thin air, I guess we would say. They were based on some type of measurement or observation from the supply chain. So what we do is sharing. That work still continues today through the standards organizations. We participate in that.
No, and it's really clear all the work and all the effort that your companies your sister's company also have in this supply chain, but also how this impact not only in this data collection or improvements or design, but it's really an impact in a bigger scale. It's like the environment, the communities, also that the e-commerce. I mean, there's a lot of things that are involved in the process that you work on. And for us, it's really an honor to have you here. We want to have you many more times. Hopefully, once that we can go back to the university, we would like to have you with us, if you agree with us. And if you're okay, so we can close right now, but we will let you know all the questions and all the comments, because there's a few of the students that had to leave, but they left their comments. No, but we really wanted you to share with us all your experience, and there's nothing more. I think, Cristina, if you would like to say something, please.
I want to say something.
Please.
Thank you, Eric, and thank you for show all of us what the big leaks are about vibration and all the techniques to see how the packaging can be behave in the transportation. And I love all the examples that you are presenting about the space and
very interesting.
And he didn't he has another cases that is very important, and I was astonished about the dinosaur. Do you remember the one that you transport? So there are so many things that sometimes we don't have in the loop, but are related to packaging. So thank you very much for that scope, and I really appreciate your participation.
As an example, let me give you one more example. I don't even know how many people are still on, but just last week, the kind of calls we get from real companies, a company here in the US that ships bulk quantities of frozen biological product, meaning medical product. Think of vaccines. One pallet load of that product has a value of $10 million. So, so you can only imagine how critical it is to make sure that their packaging design concept is going to work. One pallet load, $10 million of product on that pallet. And so if there are, 30 pallets on that, in that one truck or one container, the value is it's incredible. So it shows you how important packaging is, protective packaging and the role of protective packaging. I realize not everything is that valuable, but that's a very real example. That's just last week, someone contacting us asking for help to make sure that they don't damage that $10 million of product.
Yes, it is very important.
There's no room for mistake in this, especially in these times, with all that we are living today, is like no room for mistake. So I don't know, Cristina, if you want to say something else, but
no, thank you very much, Eric. Good
night. You're welcome. Thank you.
I think we will have to do many more of these sessions because you have a lot to share with us, and we are really grateful for the time that you designated to us, because we know you are traveling right now, and that's it for me. Thank you so much. Have a great night to everybody. And thank you so much, Eric.
Yeah, thank you. I look forward to visiting sometime, hopefully in the next year.
Please, we want to have you here. Thank you so much, Eric.
Thank you.